Hello, I am Patrick from Sumitech Turbo Machinery Solutions. The objectives of this presentation are to familiarize rotating machinery engineers involved in detailed engineering and site operation. Sensor mounting, methods of proper setting of thrust bearing end play and voting are also discussed as a part of on-site work carried out during pre-commissioning activity of mission-critical turbo machinery. The first part explains types of thrust bearings, failure mechanisms, and temperature monitoring. Upcoming second part shall explain thrust positioning, setting alarm and trip and installations. Anti-friction type thrust bearings are normally single or double row angular contact bearing, spherical roller bearing, and taper roller bearings. An anti-friction thrust bearing arrangement, back-to-back, places two bearings, so their inner rings are closer together than their outer rings, creating a wide span between their load lines. This configuration provides maximum rigidity, stability, and resistance to moment loads from shaft misalignment. The exploded view of a typical hydrodynamic thrust bearing is shown. Each bearing consists of a series of pads supported in a carrier ring, retainer. Each pad is free to tilt, resulting in a self-forming hydrodynamic film. The self-equalizing design balances the load between the pads and accommodates misalignment or deflection between the bearing and collar. The carrier ring may be in one piece or in halves, and the size and number of pads are selected to suit the operating conditions. In addition, pads can be supplied with center pivots for bidirectional running or offset pivots for increased load capacity and lower pad temperatures. There are normally two types of thrust bearings: non-equalizing and self-equalizing tilt pads, and then again tilting pad and taperland type. Tilting pad type has pivots shown in solid dots in the picture. Taperland bearings typically have about half the load capacity of tilt pad bearings. In taperland design, a converging taper is machined from the pad leading edge to somewhere near the trailing edge. While the taper is responsible for generating hydrodynamic pressure, the flat region near the trailing edge provides a surface to set the rotor float or position as well. The picture in right side shows the active and inactive sides of thrust pads. In between these, the thrust collar with shaft is positioned as shown in right side picture. The active side of a thrust bearing is the side that handles the normal operational axial load, while the inactive side is the side that does not carry the load during normal operation but acts as a backup or limits axial movement. The picture below shows a typical installation of steam turbine generator set, where the thrust bearings are located in NDE side of steam turbine. Thrust bearing load capacity rating must comply American Petroleum Institute guidelines. If the axial position of the motor at rest, mechanical center, is different from the magnetic center, the rotor of the motor may move axially to the magnetic center when running without load. This is a low-frequency phenomena and normally present in two-pole electric motors. Limited end as sleeve-bearing motor, for example, floats as the rotor hunts for the magnetic center of the winding. It is, therefore, necessary to use a coupling with limited end float. Couplings are used in such cases to avoid movements in driven shaft. A limited end float, LEF coupling, is used to prevent the axial shuttling, or unwanted back-and-forth motion, of a motor shaft that is supported by sleeve bearings. By restricting the motor's free axial movement, the coupling ensures the rotor remains in its optimal magnetic center, preventing damage and operational issues. There is generally more axial play in motors with sleeve bearing than motors with rolling element bearings. Prior to coupling sleeve bearing motors, it is a good practice to run the motor and mark the rotor position when it is in magnetic center. Then couple the motor, keeping the rotor in that magnetic center position. Angular contact bearing failure can result from improper lubrication, contamination, misalignment, fatigue, or incorrect installation, leading to issues like wear, overheating, and excessive noise. Common failure modes include skidding from insufficient preload, fretting from vibration, and wear or smearing from contamination or excessive loads. Spherical roller bearing failures are caused by issues like improper lubrication, contamination, poor installation, and excessive loads. Other causes include misalignment, overheating, and fatigue, which can manifest as wear, cracking, or spalling of the bearing surfaces. Tapered roller bearing failures are most commonly caused by poor lubrication, improper installation with very high preload, overloading, and contamination. Other causes include fatigue, corrosion, wear, and electrical damage. It is strongly advised that installations must follow OEM recommendation. This slide shows various failure modes of tilting pad hydrodynamic thrust bearings. Movement of the babbitt occurs from the region of contact, minimum film thickness, towards a region of larger film thickness. Severe wiping on a thrust shoe with circumferential scratching can be seen in most of the cases. Localized burn marks can be due to lack of proper oil fill thickness at maximum head zone. The picture in left side shows degradation of pivot contacts and leveling plate wear of the thrust shoes. The middle picture shows effect of stray current causing electrode discharge machining with deep track lines, and rightmost picture shows effect of frosting caused by same phenomena. The picture below right shows a SEM photograph of frosted surface. The picture below left shows severe damage in pad due to overload. Varnishing of thrust bearing pads is a destructive process where a hard, lacquer-like deposit builds up on the bearing surface, caused by the degradation of lubricating oil. This buildup reduces the hydrodynamic oil film thickness, increases surface roughness, and insulates the bearing, leading to higher temperatures, increased friction, and potential metal-to-metal contact and failure. Damage to tilting pad thrust bearings is caused by factors like lubrication failure, overloading, contamination, and misalignment. These lead to various damage mechanisms, including abrasion from debris, wiping or scoring from contact, overheating leading to thermal fatigue and coking, electrical discharge pitting, and damage from cavitation or pore assembly. The picture shows the temperature profile of thrust bearing pads when shaft is rotating counterclockwise. Based on this information, the RTD orientation are decided for monitoring pad temperature of thrust bearing. Sometimes only alarm function is provided. Common placement points of temperature sensors are trailing edge, middle radius, middle radius, leading edge. Middle radius points 75% from the leading edge and 75% up from the pad's inner radius. Bearing temperature excursions can cause operational disruptions. Below are some noteworthy bearing temperatures based on operational experiences and ASTM B23. 110 degrees Celsius alarm temperature, 120 degrees Celsius trip temperature, 132 degrees Celsius babbitt creep, 232 degrees Celsius babbitt melting point. It is important to sawtooth type trend of bearing pad temperature, shown in picture below, which can be a telltale sign of lubrication issue. Thrust pad RTD must be secured with RTV sealant compatible to withstand minimum 120 degrees Celsius. Note that if we use high-temperature range sealant, curing time will be longer. RTD cables are to be properly secured and strapping to be done with temperature-compatible straps. Continuity and polarity of RTD and displacement sensors cable to be checked and to be recorded in service report. Precaution are to be taken while fixing temperature sensors on pads to ensure that handing cables do not get entangled between thrust collar and truss pad. There are spring-loaded sensors available, and these types should be preferred than embedding type sensors which require high-temperature sealants. It must be noted and documented in manual that in any case if any signal is lost from any temperature sensor, the unit must be shut down and condition of cables of sensors are to be checked. The rightmost picture shows the pad damage due to entanglement of cable between thrust bearing pad and thrust collar. Watch out of part 2 of this video. Sumitec Turbomachinery Solutions is your trusted partner for all your turbomachinery needs. With our deep expertise, innovative solutions, and unwavering commitment to excellence, we empower engineers and organizations to achieve peak performance and reliability in their critical rotating systems. Let us guide you through the complexities of the turbomachinery industry and help you unlock the full potential of your equipment.